Hi, I'm Luke. I work in the iOS team. I'd like to show you a project I've been working on. This is the B3 AR, or I call it the Bear. It's a robot for physically testing the B3 hearing aids with the Lexi app. A motor operates the lid. It can open and close. There are two grippers that are operated independently. They are mounted on a vertical elevator that moves up and down to place the hearing aids in the case and take them out. Hearing aids can be in one of three states: off, on and uninitialized, or on and initialized. Placing the hearing aid in the case with the lid closed turns the hearing aid off. Opening the case turns the hearing aid on but leaves it uninitialized. Once the hearing aids are removed from the case, they become fully initialized. By using these basic operations and operating the grippers independently, the hearing aids can be put into any possible state for testing. The left hearing aid can be turned off while it is in the case with the lid closed, and the right hearing aid is turned on. And vice versa. The robot can be used in different ways to test the hardware with the application. One of the ways to do this is using a UI test as shown here. So the video on the left is showing the robot synchronized to the application running on a physical phone on the right. This is using a instrumented test, so there's an application that interacts with the Lexi app and emulates gestures such as taps and drags and so on, and inspects the UI. The main difference here is that it's also controlling the robot to set the hearing aid into a specific state. It might be that the hearing aid needs to be on or off. And then it verifies that the app is behaving as expected in those conditions. So it's going to try different scenarios, including known good cases, so such as where a hearing aid connects normally under normal conditions. It'll also exercise failure modes, such as disconnecting a hearing aid while the user is attempting to connect, all the while ensuring that the app is behaving as expected. The robot platform itself is platform agnostic. It is not specifically designed to be run with iOS. It runs on a generic ESP32 microprocessor, which is used commonly for IoT devices. It provides a HTTP interface for interacting with it. It stores all of its settings in firmware, and it also provides an MCP, or Model Context Protocol interface. So it makes it usable to any testing framework that can access the robot over the network, including Android or Appium. MCP allows the robot to be used by an AI agent such as Claude. It allows the AI agent to exercise the hearing aids while controlling the app, for example, to investigate bugs, even perform feature development. The hardware was completed last week, actually on Thursday last week. And this week I've actually been implementing some UI tests and unit tests to see what the robot could do, and also exploring using the robot with Claude and AI. Interestingly, I was able to use it to replicate bug that was discovered recently, specifically where the user has a B3 hearing aid connected and then attempts to connect to an H1, and then this leaves the app in an inconsistent state in onboarding. So Claude was able to replicate this condition, implement a fix, and then test it with the robot. Also, while doing this, though, it discovered three new issues, which have been logged as Jira tickets, and these could again be pulled into Claude, which could run it on the robot, potentially provide a fix, and then test it. The plan with this platform is to use it as a sort of a test bed to see the practical use cases and benefits, and also to study the failure modes of the robot to look at which parts wear out and at what sort of rates and that sort of thing after under continuous sort of production usage, and then also iterate and improve on the design. So this is just really a proof of concept at the moment, but it would be useful to extend it to have, say, for example, a microphone that could listen to the output of the hearing aid audio, and then analyze that inside a test. So for doing things like performing the hearing test automatically. Another useful addition would be adding small actuators on the sides, smaller servo motors that could actually press the buttons. So at the moment, we rely on removing the hearing aids from the hearing aid case and returning them to the case to turn the hearing aids on and off. But by adding motors on the side to push the buttons, we could hold down the button to turn the hearing aid on and off, as well as using the program button feature. So to push the button to change the program or to adjust the volume. To support other hearing aids, this design could support the B2 Plus quite easily, meaning with minimal modification, so it's not a full redesign. The cradle would need a different design to support the B2 case. The lid opening and closing mechanism would be pretty much the same, and the gripping mechanism for removing the hearing aids would be similar. For the B2, though, the side actuators would be essential because those only turn on and off by pushing the buttons. And there are two buttons on each hearing aid, so we would need slightly more complicated actuators to be able to push both buttons, or just push one side of the button and have those reduced or limited testing. For the Ergo hearing aids, the Ergo 8, for example, is quite easy to test physically because it's fully testable while it's in the case. So the app can connect to it, pair with it, do most of the functions while it's in the case. So having a rig for the Ergo 8, for example, is not really as necessary as it is for the B3 and the B2, but it would still be useful to have. Those could also be supported quite easily with this design. So again, with a different cradle to support the different case. And the grippers could work almost identically with using the little wires that are on those buds. It would be useful to have multiple of these platforms running. So the immediate use case would be running this as part of the nightly build. So currently our plan is to use instrumented tests and UI tests as on the nightly builds for regressions, and then the robot would naturally form part of that. Where else could be useful is by being part of the QA process. So QA testers could write tests to run specifically on the robot test harness to replicate specific scenarios, identify bugs, or even program tests for new features. It's also useful for developers. So if you, as a developer, have this on your desk, you can use it for regressions, debugging code, feature development. It's very useful to be able to replicate scenarios that are quite difficult to replicate by hand just because of the timing and repetition required, and also to do permutation testing. So if we could, for example, have these multiple rigs for and supports all the different products that are available, we could do like a full permutation test between, say, switching between all the different types of hardware using the app, simulating upgrade paths, those kind of scenarios that involve different hearing aids and not just testing the B3 in isolation. Issues that we run into have to do with, say, some of the older code, especially with the Lumen, and it would be useful to have some automation around that to ensure that new code and modern code and new hardware that's being developed is not now causing regressions in older legacy code due to cross dependencies, and shared mutable state and other sort of legacy artifacts that cause interaction between the products. In terms of cost, the machine are built with 3D printed parts, basic PLA and PETG for the structural components, hobby servo motors for the grippers and the lid, and then a stepper for the vertical axis. The total cost, I estimate, around 15,000 Rand. I started developing this, or I had the idea for this, I think, about 3 months ago. I initially built a prototype with Lego Robot Inventor. The first version was just a proof of concept, so it would open and close the case and remove one hearing aid. The second version was slightly better. It had two independently operated grippers and a more powerful lifting mechanism. It was able to remove both hearing aids and replace them in the case. While it was severely underpowered and obviously not built to be robust, it did prove the concept well enough, motivating investing more time and effort in a structurally sound prototype. I initially started with some hybrid designs, so designing some 3D printed parts that were actuated with the same electronics and motors from the Lego, even keeping the Lego dimensions. This allowed for a easier transition to the 3D printing. I settled on the design for the linkage quite early on. I'm using what's called a Roberts linkage. It's basically a almost or nearly straight line mechanism. So it takes the rotary motion of the motor and converts it into linear motion. What's nice about this is that it gives you linear motion without any sliding. So you can use cheaper bearings, and also avoid any sliding components. The entire machine is designed to be 3D printable. All the structural components are 3D printed, so no expensive, complicated machining necessary. This keeps costs very low, and also allows for rapid iteration and development. I was able to build the functioning version. It took about a week of printing, I think, spread out over the 2 months. Most of that time was waiting for delivery of parts from China. It uses about a kilogram of plastic, a combination of PETG and PLA, so no fancy plastics are needed. White pads on the grippers I made with silicon rubber, which I cast into 3D printed molds. To prevent plastic deformation, I use small 5 millimeter bearings on 2 millimeter axles. The idea is that the 5 millimeter radius will spread the load within the plastic to prevent that long-term deformation and leading to backlash. But I'm also considering using 3D printed nylon bushings, and that would greatly reduce the cost of the bearings. So the cost of the bearings, they're about 7 Rand each. And I use many. So I think there's about 80 bearings per gripper. The single biggest cost, I think, is the stepper motor and the screw thread. I overestimated the size of this one. I used a 300 millimeter one, but I could probably have gotten away with 200 millimeter or less. The total travel of the gripper or the vertical axis is about 130 millimeters. Hobby servos are not known for longevity. I might switch to using steppers and screw thread for the grippers as well, and a stepper for the lid. The second unexpected turnout from this was I planned on using a Raspberry Pi for the requirements of having a web server and driving multiple motors and that sort of thing. My Raspberry Pi got lost in the post, so I ended up using the ESP32, which is a lot less expensive. And the ESP32 is fine. It runs the robot at the performance that it needs to. It can run the web server. That's all I have to show for right now. I hope you found it interesting. Thanks for watching.